Okay, folks, continuing along. So we've discussed the thermodynamic definition of entropy. Now, let's get into the statistical definition of entropy. So as you might guess, this is going to involve a little bit of statistical mechanics, but just a brief conceptual overview. So to get into thinking about the statistical definition of entropy, we have to introduce this concept of an ensemble. So an ensemble is a collection of a number of particles with identical properties that overall describe the macroscopic state of our system. So there are three different types of ensembles that we can describe. And this first one is the canonical. And in the canonical ensemble, we create a box, okay, that can be replicated I number of times. So we'll say replicated. So we can have it like over and over and over again. And in this system that we're replicating, the number of molecules, the volume, and the temperature are all identical. So for this to be true, that means we could describe the canonical system as a closed system, right? So the only way the number of molecules and the volume can remain the same, of course, is as if no mass is allowed to get in and out. And of course, the only way for the temperature to remain the same is if it is free to exchange heat with all of these other replicates. So we can think of like another ensemble or another collection, I should say, being next to it. And because these things are next to each other, they are allowed to exchange heat such that the temperature remains the same. Another type of ensemble that we could describe is the microcanonical. And in the microcanonical, as you can see, the number of particles and the volume remains fixed. However, the energy of each identical replicate has to remain fixed. And so what that means is the microcanonical, oops, I was going to write open, but that's not correct. The microcanonical represents an isolated system, right? The only way that the energy can remain fixed is if it's not free to exchange heat with its neighbors. And of course, the last type of ensemble we could describe is the grand canonical. And in the grand canonical, temperature and volume remain fixed. However, this component that we haven't introduced yet, called chemical potential, remains fixed. And for the chemical potential to remain fixed, it has to be able to exchange mass from system to surroundings. So this grand canonical is a fancy way of saying that it is an open system. We will predominantly deal with the canonical ensemble, and this whole concept of ensembles is really quite an advanced concept in statistical mechanics. So this is just a brief introduction to this concept, but it's important we recognize what these are, as they help us create the basis of what we call the microstate. So here's a better way that we can view what a microstate is. So imagine we've got 4 molecules and we can place them in this 2-bulb flask. We note that there's several ways to do this. For example, we could have all 4 in flask 1 on the left flask and none on the rightmost flask. And then of course we could rearrange them according to the following pictures. So each of these arrangements would represent a macrostate. If we get really specific now and start looking at the labels and the positions of each of these molecules, we can now begin to understand the concept of this ensemble. In other words, all of these particles being in contact with each other and how they might contribute to the overall macrostate. So for example, let's suppose I put labels and positions on these particles, A, B, C, and D. So now this one arrangement right here truly is just one arrangement. However, if we now make 3 and 1, 3 on the left, 1 on the right, and considering their labels and positions, we can get 4 different microstates out of that. So in other words, the way in which an A is in contact with a B or a C or a D would be different. Okay, so for example, I can have an A that's not in contact with any of them, and then a B, C, and D on one side. Or I can have a B that's not in contact with any of its other identical particles. And then on the other side, it'd be a C, A, and D, and so forth. Our arrangement with 2 and 2 could create 6 possible microstates. With 3 and 1, that would be different than this arrangement 2 because we're considering those positions relative to each other. So overall, if we count up how many microstates we could get from this thing, we sum all of these possibilities up for each given macrostate. So for this example, that would be 1 plus 10 makes 11, 15, so that would make 16, microstates in total. Okay, so counting up to 16 microstates from our 4-molecule system wasn't too particularly challenging. However, if we want to consider more realistic amounts, like a mole of molecules, there's no way we're going to be able to count. So Boltzmann proposed this equation here, and I'm not going to go through the derivation. It's rooted in statistical mechanics. And in this equation, instead of trying to count the number of microstates, we can determine them by knowing the entropy of the system. Okay? So in this famous equation, which actually appears on Boltzmann's tombstone, there it is, K log W, entropy can be related to this concept of microstates in the following way. Boltzmann's constant times the natural log times the number of microstates, W. And so now we can kind of start to think of a better definition for what this microstates means. The number of ways in which the molecules of a system can be distributed over the energy states for a specified total energy. So it's all about our population of states and how those populations are distributed to maintain one of those types of ensembles, depending on what we're talking about. In the case of the canonical ensemble, the way in which our populations are distributed over the available energy to maintain a constant temperature, volume, and number of particles, for example, in the canonical ensemble. Okay? And so when we start, we'll do some calculations of this in the live lecture, but in effect, by measuring entropy, so that's what we seek to do, measure entropy, microstates can be determined. Okay? And this is much more in line with our common understanding, or a common way we view entropy as increase in number of microstates owes to an increase in entropy. Or in other words, a large number of ways of arranging things gives us a large entropy, which is kind of where we get that viewpoint of entropy is a metric of disorder. Really, it's a metric of the number of ways things can be arranged. Okay? So if we move along here, last slide of this lecture, we can view the way in which the microstates or entropy of a system changes with things like changing temperature or changing volume. So for example here, this would be change in T. And if we imagine that we've already got something at a high temperature, so this is our initial and this is our final. So there's two examples here, a high temperature example and a low temperature example. Okay? So if we add heat to this system that already has a large distribution of states over the given available energy levels, we can see more microstates. So we've populated the states more, right? Like this was unpopulated right here and now has become populated at a higher temperature. But overall, it doesn't look like as drastic of a change. Now, if we look at this low temperature example from some initial to some final state, okay, in this low temperature example, it's got a very ordered or very regular distribution of states. So this would be a small number of microstates here. Okay. But now we add heat, and you can see our population of states is vastly different. So low temperature samples will respond to an increase in entropy much more readily than high temperature samples. Another way that we could view this, for example, change in volume. So if we fix the energy of our system, but we allow it to expand, we could do some calculations with the Boltzmann distribution and show that as we expand the volume of this system, the energy states become more crunched together, right? Just imagine taking this thing and spreading it out, okay? So our energy states will get closer together, and this will actually allow us to populate more. So for example, if we only had a couple of these states distributed, because of their spacings, right? The higher they are, the less likely they're going to get populated. But now as we spread them out and crunch the energy levels down together, we're going to be able to populate a lot more of these states because we've allowed them to get closer together. So in effect, by changing the volume, we're increasing entropy, right? Increase in entropy. And in contrast to the thermodynamic view, where we just looked at changes in entropy, this statistical view allows us to calculate the entropy directly at any given state, given the number of microstates that it has. Okay, so that's some pretty heavy stuff, and we'll go through some calculations on this in the live lecture. I'll see you then.